Have you ever just looked up at the night sky and wondered, how far away are those stars? I mean, really. It's a question that's been on our minds for, well, forever. Today, we're going to dive into one of the cleverest tricks astronomers have up their sleeves for measuring the unbelievable distances across our universe. And it all kicks off with a pretty simple puzzle. You know, when we look up, we see this incredible, sprawling view. Some stars are blazing bright, others are just tiny little specks. If you're lucky, you can see these amazing cosmic clouds, maybe even the Milky Way itself arching overhead. But all of that beauty hides a fundamental challenge for us down here on Earth. And yeah, that's the big question, right? A star that looks kind of dim could actually be a super powerful giant that's just ridiculously far away. And a really bright star? Well, it might just be our cosmic next-door neighbor. So how in the world do we tell the difference from our little vantage point? To crack this problem, we first need to get our heads around two really important ideas. It's all about separating how bright a star really is from how bright it looks to us. Let's break it down.
Okay, first up, we have luminosity. The easiest way to think about this is like the wattage on a light bulb. A 100-watt bulb is always putting out 100 watts of power, period. Luminosity is a star's true wattage, the total energy it's blasting out into space every single second. That value is fixed. It doesn't change no matter where you are in the universe. Then you've got radiant flux intensity. So if luminosity is the bulb's real wattage, this is how bright that bulb appears from wherever you're standing. It's the piece of that star's power that actually hits our telescopes here on Earth. And you guessed it, this one depends entirely on how far away you are. So here's the absolute key takeaway. Luminosity is intrinsic. It's the star's real deal. Radiant flux intensity, or apparent brightness, is what we actually see and measure, and it gets weaker and weaker with distance. Why? Well, a star's light has to spread out as it travels across space. Think about it like this. A star is sending out light in every direction at once, creating this huge, expanding bubble of light. As that bubble, or sphere, gets bigger, the same amount of energy is stretched over a much, much larger area. So if you double your distance from the star, that light is now spread out over 4 times the area, which means it looks only 1/4 as bright. Triple the distance, and it's 1/9 as bright. That's the inverse square law, and it is crucial. And all three of these concepts, apparent brightness, true brightness, and distance, they're all tied together by this one beautiful, simple equation. The apparent brightness we measure, which we call F, is equal to the star's true luminosity, L, divided by the surface area of that light sphere at our distance, which is 4 pi d squared. This formula is everything. Okay, so with our telescopes, we can measure F, the apparent brightness, no problem. But to find the distance, D, we're still missing L, the star's true brightness. This was the big hurdle. And this is where astronomers had an absolute stroke of genius. They realized they needed some kind of cosmic yardstick. And they called this yardstick a standard candle. A standard candle is any object out there in space where we somehow know its true intrinsic luminosity. Think about it. If you know you're looking at a 100-watt bulb and you can measure how dim it looks, you can figure out exactly how far away it is. It's a simple idea with universe-changing implications. And the method is just perfectly logical. Step 1, find one of these standard candles out in the cosmos. Step 2, point your telescope at it and carefully measure its apparent brightness, F. Step 3, you grab your known value for L, your measured value for F, and you plug them right into that inverse square law equation, and voila, step 4, you solve for D, the distance. Let's actually run through some numbers. So let's start with a little warm-up using something we know really well, our sun. We know its true luminosity. It's a mind-boggling 3.9 times 10 to the 26th watts. And of course, we know how far away we are. So let's use the formula to double-check how bright it should look to us here on Earth. We just plug in the luminosity and our distance, do the math, and we get about 1,400 watts per square meter. Now, that's not just some random number. That's what scientists call the solar constant. It's the real amounts of solar energy hitting the top of our atmosphere. So hey, our formula works perfectly. Okay, now for the real magic trick. We have a standard candle, a type of star called a Cepheid variable. We know its true luminosity is a whopping 4.6 times 10 to the 15th watts. But from Earth, what we measure is this unbelievably faint glimmer of light, just 1.3 times 10 to the negative 23rd watts per square meter. The mission is clear. We know L, we've measured F, now we can find its true distance.
We rearrange the formula a bit, plug in the numbers, and the answer is just astounding. We get 5.3 times 10 to the 18th meters. To put that in perspective, that's about 560 light years away. And just like that, using a standard candle and a bit of math, we've just measured a distance that is almost impossible to comprehend.
I mean, this is an incredibly powerful tool, right? But the whole thing depends on actually finding these standard candles. So what are these special objects that let us in on the secret of their true brightness? Let's meet the most important tools in the Cosmic Detectives Toolkit.
Now, astronomers use a few different types, but there are two that are the absolute A-listers, the rock stars of measuring cosmic distance: Cepheid variable stars and these insane explosions called Type I supernovae. Cepheid variables are just fascinating. These are stars that physically pulse. They get bigger and smaller, brighter and dimmer on a super regular schedule. Way back in the early 1900s, an astronomer named Henrietta Leavitt made a world-changing discovery. She found a direct link, like clockwork, between how long it takes a Cepheid to pulse and its true luminosity. You can see it in the graph. The longer the period, the brighter the star really is. It's like a cosmic metronome that tells you its power. But what if you want to measure the distance to another galaxy, billions of light years away? For that, you need something way, way brighter. And that's where the Type Ia supernova comes in. This isn't just a star. It's a star that explodes with such violence that for a few weeks, it can literally outshine its entire galaxy. At their peak, they can reach a luminosity of around 10 to the 36th watts. That's 10 billion times brighter than our sun. But here's the real kicker. Because all Type Ia supernovae are triggered in the exact same way, they all explode with almost the exact same peak luminosity. They are incredibly bright and incredibly reliable standard candles that we can spot from clear across the observable universe. So, we've got the tools and we've got the technique. But what's the big deal? What has this ability to measure distance actually done for us? Well, the consequences have been nothing short of revolutionary. Standard candles are basically the foundation of modern cosmology. They let us map our own galaxy for the first time. They gave us the distances to other galaxies, which led Edwin Hubble to discover that the universe is expanding. And then, in the 1990s, by looking at super distant Type Ia supernova, astronomers made the shocking discovery that the expansion of the universe is actually speeding up, which gave us the first real evidence for this mysterious thing we now call dark energy. Of course, it's not a perfect system. There are some practical challenges. Not every single standard candle is a perfect clone of the others, so there's a little bit of wiggle room. A bigger issue is cosmic dust. Dust floating between us and a star can block some of its light, making it look dimmer and therefore farther away than it really is. And the whole distance ladder relies on getting super precise measurements of the candles closest to us, which is a really tough job. So from what seems like a simple question, how bright is that star? We figured out a way to map the entire cosmos. These standard candles have been like lighthouses for us, guiding us through the cosmic ocean. They've shown us a universe that's not just huge, but one that's alive, dynamic, and expanding faster every second. It really makes you wonder, what other incredible secrets are just waiting out there for us to find the next candle to light the way?